Okay, puzzling air pockets and complex ice crystal growth forms. Results from a new experimental apparatus. This is work that I did with Brian Swanson. We received funding from the NSF and the Laux Foundation, and it was administered through the UW. We also seek support through GFM, which is GoFundMe. I will explain more about that at the end. Now, Brian tells me that probably you haven't seen a ice microphysics seminar in a while, and I should spend more time on the background. So I thought I'd go back, and it seemed appropriate to start with Bentley. I mean, he was a guy that really popularized snow crystals. He's famous for the saying, no two alike, but he was also a very keen observer. He observed many things that, say, even now, scientists haven't examined. But one of them that I'm going to talk about today is he was pointing out these little circles in the center of some of these. They're in some, but they're not in all. Anyway, yes, I will talk about those later. He called these micro photographs of snow crystals here. This was his first major work, 20 years study of snow crystals, but micro photographs would in fact be too small to see. He later corrected that to photomicrographs in his later publications. Probably the scientist that contributed the most knowledge about snow was Ukichiro Nakia. He was influenced by Bentley, and he's known for a few things. One is he was the first guy to grow the artificial snow crystal in the laboratory. And when he did this, he did this under many conditions. He produced a diagram, and here's an example of an early diagram, 1958. The bottom shows air temperature. The vertical is humidity. These are not percent, but it's increasing humidity. And the different crystal forms. He found that they were reproducible. So he said, that this means that you could look at a crystal and infer where it came from. And he kind of coined this neat little expression, a snow crystal's letter from the sky. I have colored in these ones here, the scroll forms near -5 or near the needles, and this blue region here, the dendrites. I'll talk more about those later. Another thing that Nakia did was he produced one of the first classifications, pretty extensive one. It had 41 ice types, and that was 1954. 1966, Magono and Lee, and they were at the same institution as Nakia. They expanded the classification to 80. Magono became very well known for other work on snow crystals. Lee was his student, and although this paper was a very famous paper, Magono and Lee, Lee just kind of disappeared. He went back to his home country, North Korea, and I don't think anybody really heard from him again. A lot of people have used Magono and Lee, but more recently, an even larger classification was proposed in 2013 by Kikuchi Kameya, Higuchi Yamashita. And I won't talk much about this, but one thing they include is the aggregates down here. These are, in fact, probably the crystal form we see the most. These are the snowflakes, the individual crystals that all kind of clump together into these big blobby things. Also, the note that perhaps the main division here is that people make is between the columnar and the planar. And what this is a measure of the axial length to the axial diameter. So this is a key characteristic. Continuing with this background information, in fact, these dimensions are what is usually measured in the laboratory. And what this is a measure of the facet advance. And consider these sketches here. This is the basic form, a hexagonal prism. And as the faces collect molecules, they advance normal to themselves. So these crystal growth, call this normal growth. Some atmospheric scientists call it linear growth, but I'll refer to it as normal growth rate, or just the N-type growth. And this gives the increase in the crystal size. So the normal growth describes the facet advance. It also will apply to non-facets, but we focus on facets. How do these facets advance? Well, even though the facet looks very flat, if you look very close with a high enough powered microscope, you'd see that in fact it is stepped. There are these incomplete layers, and these layers have to be generated and then they have to move across. So this shows what we think is the most common situation, layer nucleation at a corner. A step or layer is nucleated here, just like three-dimensional nucleation. They cluster and become stable and then grow, and they grow out, and then the region where it had started now can produce a new one, and that is produced, and this continues. If you look at the whole crystal face, these will be coming from the edge on both sides, and the steps are going in towards the center. As they go in towards the center, now the usual situation is this, and they're coming from the edge because that has the highest supersaturation and the center has the lowest. So as they come in, they go into region of lower supersaturation, and that's marked on this little sketch to the right. Now if they have a lower supersaturation, they'll go slower. So they slow down, and the guy comes up behind it going faster, and so it gets closer. And so these steps get closer as they get closer to the center. That means that their efficiency at collecting molecules increases, but efficiency can only reach 100% or 1. And if this supersaturation decreases even more in the center, then the surface can't keep up. And instead of now looking like macroscopically flat, a little hole will develop, a little hollow. So, and this is what probably happens in all leading crystal facets. They'll initially flat, but eventually, if they're growing in the air, they will hollow like this, and the hollow will be in the center. How do these steps get started? I mentioned that the accepted view, I think it's pretty well accepted, at least mid-length to high supersaturations, is layer nucleation. Now, people were convinced that snow crystals must be growing by layer nucleation for a long time. Scientists like Charlie Knight, Charles Frank, Akira Yamashita, but there wasn't any real good evidence, measurements that of the key characteristic of layer nucleation, and this characteristic is the critical supersaturation. So I was working in Charlie Knight's laboratory and was looking at other things, but noticed this critical supersaturation, and I started changing the temperature and measuring it at different temperatures, and ended up with a plot like this, and I was real excited. I showed it to him. I said, "Well, look, this data, it's just like what Charles Frank was arguing," and Charlie pointed out that, in fact, it was he who had published the earlier paper arguing strongly for layer nucleation. It was kind of an obscure journal, and Charlie told me why, but anyway, that's a long story. At any rate, this is consistent with the observed habits, but another other interesting thing is that the real joker here is the basal phase. This is the one that varies the most. It's high, critical value. At warmest temperature, goes down to minimum, and then goes back high. Don't really know why it has a minimum, but it does, and the fact that it does means that it crosses that of the prism in two places. And this is just right about where we see the columns and the planar forms make a transition. So this is consistent with that. It's also consistent with some earlier measurements showing that other parameters, such as what I showed in the previous back here, I didn't mention this. This XS, this is the surface migration distance that a molecule travels before leaving. That had been measured earlier on the basal phase and found to have this strong temperature dependence. Very similar to this, and same with the step speeds. So this was nice. It all kind of fits together. But even so, you know, one can use these ideas, normal growth and the layer nucleation, and explain a lot of things about observed crystals. But there's also quite a bit, if you look closely, you see you can explain with normal growth. The scroll, if you look at the scroll, this is kind of like a sheet of paper that has been folded around, curling around inward, just like rolling a scroll. That's why they call it a scroll. The trigonal, here we're looking down the axial direction. This could be like a columnar, and you're looking at a cross section. Also could be tabular, but it only really shows 3 prism faces. The sheath cluster, or bundle of sheaths, it's a single crystal. I mean, it looked like kind of a hodgepodge there, but single crystal, but it has these like sudden jumps in diameter, and you really don't expect from normal growth, where these are growing, you shouldn't have the prism face growing normally. So what causes these sudden jumps? The hollow column is a very, very common crystal, and I showed the hollowing before in the previous slide, and that can be explained by normal growth, but these bands, how do you explain those? Not by normal growth. Okay, so this is just a few. In the paper we look at a number more of them. We set out actually to look at normal growth rates, the normal growth mechanism, you know, like at low supersaturations below the critical value. Now defects can start controlling growth. So we want to find out when that occurred and sort of the different types of defects, hollowing. But the existing apparatuses had a lot of artifacts. Now, the one that I used before for the critical supersaturation measurements, that was actually quite good because the crystals grew on a very, very fine glass capillary. So this could hold the crystal steady, but had minimal contact. I mean, that capillary could be less than 5 microns. So that's minimal contact, but it's held steady. You get great pictures that way. We wanted precise control of the conditions. We had it in that previous capillary apparatus, but we also wanted to quickly change conditions, which is something we couldn't do before. Wanted highly uniform conditions and long-term stability so you can grow at low growth rates for a very long time. We had that before, but we also wanted to have it here and also to go to lower temperatures. We wanted to be able to move and manipulate the crystals. You rotate them so that you can see all sides of the crystal. And we thought, well, wouldn't it be nice if we had more than one and we could move them closer or further apart? Well, we were so attracted by that idea, we decided, well, why not have not just two, why not have three? And so that's these CH capillary holders, 1, 2, 3. So we can study interactions between crystals and also control over the growth mode. Here's Brian in the laboratory looking through our built apparatus connected to all the goodies. It's a great lab. I think anytime you start doing experiments on ice, you're going to see strange things. You're going to see unexpected things. And at least if you know what's normal, then you recognize what is abnormal. And this was one thing that we saw kind of early on. This is a sequence of a crystal. We're showing the side view. Here's the capillary coming in. And it's rounded like this because it had been sublimated. But now it's under a growth mode and it is starting to sharpen. And a little bit later, sharpen. And now it's quite sharp. And we turn it and look at it from the front, and we see something odd here in the corners. These are pockets, air pockets. And the first time we grew this crystal, this what I'm showing here is the second time. First time, these were really faint, and when I looked at it, I thought, wow, it's like a blemish. Maybe I can ignore that, but why is it in all 6 corners? Something's going on. But with this apparatus, we can change the conditions and we can now resublimate it and then regrow it again. And that's what we did. And the same thing happened. This time, I think because we sublimated it for longer, these became more distinct. And so these are the air pockets in the corners. There's one in each corner. So if you turn it a little bit, you can see there's front and back side there. But as I pointed out, the place where you expect the hollows to form is in the crystal centers, and the hollow is sort of a first step towards a pocket. Okay, so that was puzzling. That was something that we saw actually time and time again whenever we sublimated and regrew. Now I'm showing just kind of a sampling of different findings. This is the same crystal but an earlier run, and this one shows this circle here. This is the basal facet. It's expanding over a rounded form because it had been sublimated, and this facet edge we saw expand outward until it reached the outside. This image down here, F, shows circles where that facet edge was at different times. And over here on the right, we plot that. So going to the right, that's elapsed time, and then this is the radius going up. Okay, now we compare this to 3 models. These 2 down here are just normal growth. And there's 2 types, or 2 parts that can be growing normally. One is the edge. Now if you just look at the facet edge and say this is a facet on the edge and it's receiving vapor deposition, and so it's growing normally outward due to that. That produces, over this 4,000 seconds, very little growth, almost none. This is essentially flat. If we assume instead that the facet is expanding because the rough region beyond the facet is growing normally, that produces a little bit faster, but it's still much less than the observations. And this case 2 fits the data very well. This case 2 is what we call the F-type growth due to AST, and AST is the molecular migration over the facet edge. So that's that. Now, as I said, that we would see corner pockets every time we sublimated and regrew. It didn't matter what the shape of the crystal was. Here's irregular hexagon shape, and you can count them here. 1, 2, 3, 4, 5, 6. These are all once right at the corners. And if you turn the crystal sideways, you can see that each one is a pair. So those are the 12 corner pockets there. There's also these hollows. Each face has a hollow, but as this crystal grew under constant conditions, some of these closed up. These are center pockets. They closed up. These ones over here are still hollows. And this is a real unusual one. It was a very small hollow and it never closed up. And it's on a very small face that is growing relatively rapidly. We went back and looked at the literature and noticed that, in fact, these corner pockets do appear in the literature. However, they were not noted. This one on the left is from Kobayashi and Otake. It's a crystal grown on a substrate. It was sublimated. You can see this kind of rounded, but now it's starting to regrow. You see the prism facets growing, the F-type growth, the facets spreading, the basal in side view, and then in between you see these other facets, the pyramidal facets. And when those completely expand out, you get this sharp form, but you have these corner pockets. And I thought it was interesting that these are clear as day, but he didn't say anything, nothing at all about these. And I think if you're not looking for something, you don't see it. And so maybe he just didn't see it, or he thought, well, that's curious, but they're so small, they don't mean anything, or they're just mystifying, you know. I looked also at Magono and Lee, and they have a very clear case too in their collection, but in their paper they say nothing about those. You can look at collected crystals at the ground, like this snow crystal, and if you zoom in on the center, you see that this has a little pocket at each corner. Martin Schneider heard about our work, and he had seen something similar, and he sent us this picture. This is taking from an aircraft that collected crystals as it was flying rapidly through the cloud. I forgot the temperature. It was rather cold, and this is rather high cloud, but it does look like this one has the corner pockets. It's not very sharp, but when you're flying at 200 miles an hour or whatever, it's hard to take sharp pictures. Now, what this tells us, though, is if this is anything like what we did in the lab, it required sublimation. So this suggests that these crystals underwent a period of sublimation and then regrew. So it's like what Nakai was saying. It's a letter from the sky telling us about sublimation. Here's an explanation for the corner pockets. The sketches here show some corners there, and a cross section through one prism edge. So this is during growth with sublimation, and this would be sublimation in air. the crystal around. Okay, that's one thing that we found in previous experiments. Other people have found it, that sublimation in the air rounds the edges. And then the crystal starts growing again. The facet starts spreading, so you have F-type growth. Now, something strange seems to happen in that this lateral spreading produces protrusions. This type of protrusion was coined, protruding growth by Akira Yamashita. He studied it recently, suggested it for some other situations, and it seems to explain what's happening here. Protrusions coming from the top and from the side, and they come together, and when they come together they seal up, and then there's a little remaining air pocket there. This happens at every corner, so there's 12 corners, so 12 pockets. So this is just a simple way that the P type or protrusion growth causes corner pockets. So we don't have clear measurements showing the steps there, but we can look at some other experiments and see observed F and P type growth. So these types of growth do happen, and these are from Yamashita's cloud chamber experiments. They were taken a while ago, and he sent them to us, and I think some of these appear in a recent paper of his. But on the left here we see droxtels, and these are relatively large droxtels, about 40 microns across. Each one of these four are different, but in his experiment they fell through the cloud and fell into cold silicon oil that kept them from deteriorating any further, and you could get close and observe them with a microscope. You see a basal face on top with a little edge front. The prism faces here in the front, and in between, marked by an arrow, are pyramidal. There's a pyramidal. And once again, these are all different. Notice that these boundaries are they're not straight. They're not faceted. So we think this is important. Over here on the right, these crystals grew a little bit longer and developed protrusions at the top and bottom of the droxtel. Also on little rime droplets that landed on the crystal, those produce protrusions. So in this one, you see it, protrusions on top and bottom. The droxtel in the center remains about the same. It just has these P-type growths on both sides. And down here, also on the rime and the regular crystal. So the fact that these types of growth do occur in a way that is consistent with our mechanism, it supports the mechanism, but further tests are clearly needed. Okay, so now let's go to some of the applications. I'm just going to go over a few applications. The paper has quite a few more. We're going to get back to Bentley's observation. He saw in some of these planar branch forms the circular center. Okay, here are two, McGonagall Lee and from Marcassino. You see the little circle in the middle. He said, well, these are the original droplet that froze. But if you think about normal growth, the normal growth, the molecule just build into the surface and cause the surface to expand. So it just keeps on going out. You don't leave behind an earlier surface because you're covering it up as it grows. So the existence of these is not consistent with N-type growth. And in fact, I just showed you a picture of cases with droxtels with these protrusions on top and bottom. So that naturally leads to this explanation. You have your droxel, and you have your F-type growth on top and bottom, but only on the top and bottom, the basal faces. At least it occurs there first, and then that gets develops into the protrusion growth, P-type. And after it does this, it's shadowing the prism, so that nothing ever happens down there. They continue growing out, but you can see the at least the perimeter, if you're looking down on it, has stayed the same. So it's a simple explanation. P-type lateral growth explains those. And as I said earlier, this doesn't happen to all of the planar branch crystals, just some. I think probably the reason it happens on some, not all, is that this is would be more common when the droxel is larger and the supersaturation is larger. And the key thing actually is not the supersaturation itself, but the gradient. And I think it's the gradient in supersaturation across this facet edge that leads to protrusion. So that needs to be tested. Okay, to the scroll and the sheath form. This is a little bit more involved. Maybe I won't be able to explain it completely satisfactory to you, but we argue that this requires all three types of growth. Now, a sheath starts, at least it's been seen in experiments, from the edge of a prism face. So you're looking axially down the axial axis, and this is the basal face, and here's a prism, and there's a prism. This darker region is where it's sticking up. It's protruding. This produces a sheath, and you could just picture folding a piece of paper and standing up on the table, looking down on it, and that's kind of what you're seeing, like this. But the protrusion also grows out laterally this way. Now, as it thickens, the inside will be growing by N-type growth, rough growth, but it's still N-type. It's thickening, and that's going to slow down this protruding rate because all the AST molecules are going over a larger region here. And what we think happens, and this is consistent with a lot of different experiments, is that when you have a very thin crystal form, it can have a rounded perimeter. But when that gets thicker, that perimeter will facet. We saw in the F-type facet spreading, the perimeter was round. It was like a circle. So this is rough. But if it gets thicker, then that edge will facet. And so once that facets, now the protruding growth this way stops, but it can continue now on this new facet, and that's what is shown here. So the facet has bent, but it continues. This will thicken, that will facet, and then the protrusion will go this way, and so on. So it tends to curl around like a scroll. Down here, sometimes the scroll makes a complete rim, but it's a very thin, it can be a very thin rim, and some sort of asymmetry, if it develops, will cause it to break or to hollow on one side. Once that happens, it's just like what we had above, that it will thicken by N growth, and when that thickens enough, there's a facet here, and a facet then leads to the protrusion growth along that facet, and it grows inward like so. And this is just like the scroll picture that I showed earlier. The sheath bundle starts the same, but this P-type growth can overshoot. It can overshoot the base that it was growing off of. Why would it do that? Well, the conditions might be just high supersaturations out here, and it's growing more rapidly, or the migration distance at this particular temperature is a little bit larger. Okay, so it overshoots. So what that means now, though, is if you turn this now sideways and look at like the column, just like in our picture, there's a sudden jump in width. And so this is not normal growth, because at these temperatures, at these form, the prism face normal growth is very small. So it's not normal growth, but it can be this lateral growth that causes it to suddenly widen like this. And that can continue. Whoops. Okay, finally, the last thing I'll consider is the common center pocket. If you think about it, a center pocket has to have first been a hollow. But then how does that hollow close up? Well, it has to be a rim on both sides that come in together. Now, if this is normal growth, as those two rim faces come together, get closer and closer, there's less and less vapor between them, and this is the source of normal growth, the vapor deposition there. So it'll go slower and slower and reach a point where they can't merge. So what is needed is a way for the molecule to come across the top surface and fill that in. This is the AST, and it's I think a good example of protruding growth. So we looked into this, and we argue that if you look here at the hollow edge, okay, this is the top sketch, if the normal growth rate, this dz dt, is very small, then the protruding growth rate, this dy dt, is unstable. That is, if you get a little protrusion coming out, a little bit of p-type growth, then as it grows, it has a larger and larger area to collect from, and that even drives it faster. So it's, at least at the low normal growth rates, it can be unstable to this p-type growth. And we think this is consistent with observations, because the different faces will do different things, kind of as if they have a very sensitive dependence on the conditions, like an instability. And that we think explains this, but it's a really, right now, a very crude theory. So that's it for the applications. There's more in the paper, and we get to the closing take-home message. So if you're stumped by crystal form, don't just think normal growth, think lateral growth. Think laterally. Here's the first page of the paper we have on this, and some of our peer reviews. These are pretty good. Now, our grant ran out, so we actually started a GoFundMe to help pay the page charges. There's more about that, and some, I think, interesting articles on snow and ice at my blog here, Story of Snow. Thank you for listening.